All right, so let's go ahead and do an example. This example has to do with rolling without slipping. So I'm just going to work through this, and hopefully you'll be able to apply this understanding to some of your tasks later in the lesson. So we've got a solid cylinder, and remember the equation for the rotational inertia of a solid cylinder is I equals mr. Oh wait, no, that's not right. A solid cylinder is 1/2 mr squared. Same as a disk. With a radius r and mass m, it rolls without slipping down an incline that makes an angle theta with the horizontal. And I just want to point out, I do not expect you to memorize these equations for different rigid objects. You should be able to reason through why like a cylinder has a different beta value or fraction there than like a hoop, and you should be able to tell me which one has higher rotational inertia or a higher fraction out in front. But you don't need to like memorize all of them. Like for example, on a test, I would give you the rotational inertia equation for a certain object if you had to do any calculations. Okay, so we're looking for the translational and the angular acceleration of the object and the force of static friction acting on the object. So let's go ahead and really we're going to have to kind of solve these parts together. So as a starting point, let's just draw the different forces acting on our object and the points at which they act. So we're going to have, first off, just gravity acting down. Maybe I'll use my line tool. And that's going to be acting in the center. So gravity will be acting that way. And let's call it mg. We're also going to have normal force. And normal force is going to be acting towards the object right there in. And then there's also going to be friction, and friction is going to be pointing that way. It's probably shouldn't be quite that big. Whatever, something like that. And there is our, oh, I don't like it. It's not quite the right direction, right? It should be exactly parallel to that. And I think I'm going to have to just give up and go with whatever it's given me. Okay, so that's our friction force. Now, if we were to put these on just a free body diagram, right, it would look something like that. There's our dot. We would have normal force this way. Wait, no, we wouldn't. We would have normal force that way, mg down, and we would have friction kind of off in that direction. And then if we go back to what we learned about inclined planes, right, we would know that for that mg, we would have to break that into two components. And right, this component of mg would cancel with normal force. And then this component of mg is what's pulling it down the incline. That would be a little bit greater than the frictional force, assuming it's going down the incline. So, all right, so this is what our forces look like. And now let's try to write some equations. So we can write one equation using the net force, right? So we can use Newton's second law for translational motion or linear motion, right? Same. Right, so we could write an equation using this. And then we can also write an equation using Newton's second law, using Newton's second law for rotations. Right, there's basically two equations we can develop. So let's start with just Newton's second law for translational motion. So for that, we would have a force down the incline. Right, there's going to be no net force in the direction that's perpendicular, but there is net force in the direction that's parallel to the incline. And that net force that's parallel to the incline is going to have an mg sine theta going down the incline. Right, that's this component. And then there's going to be friction pointing up the incline. And this is actually going to be a little bit greater than that. My diagram was misleading, right? This looks like it's longer than that. But this component should be greater. So for my net force equals ma equation, we will have mg sine theta minus friction force equals ma. And I just want to point out very briefly that in this equation here, right, this friction force, that is static friction, right? Because this is rolling without slipping, right? That bottom edge is not sliding. Right? Remember, it comes to rest the moment that, right, if we pick a point on the wheel, the moment that it touches the ground, it's actually at rest, so it's not sliding. That means that we can't use anything like this, right? Because that equation really only worked for kinetic friction. And for static friction, remember the equation was actually, this is for kinetic. For static friction, the equation actually had, it wasn't an equal sign there, it was a less than, right? So we don't know that this force of static friction is actually at its maximum value when something is rolling. So we can't really use this approach with mu to do anything in this context because it's static friction. Okay, so we've got our one equation using Newton's second law for translational motion. Now let's try to write another equation using the rotational motion of this object. So if we look at our forces, right, mg acts at the center, and this is where the rotation axis is, right? This is my rotation axis. So mg is not going to exert any torque because it's at the rotation axis. Now similarly, if we look at the normal force, right, this is, you could think about a moment arm as existing right about there. Right, here's my moment arm to the point where normal force and friction act. Normal force is actually pushing just right directly towards my axis of rotation. So normal force is not exerting any torque either. The only force exerting a torque is this friction force, F. So in my net torque equals I alpha equation, I'll have the net torque from friction, which is R, right, the length of the moment arm. Make my size the same. R times F, that's the torque due to friction, and that should be equal to I alpha. So I've got two equations, one using net force and one using net torque. And now, basically, we just have to go in and we have to start solving. So there's kind of three unknowns, right? The angular acceleration of the object, the translational acceleration of the object, and the force of static friction. Here I've got two equations, but I have another one too, right? So I can relate the angular acceleration to the linear acceleration through this. So I've got my three equations, and now I should be able to solve. So let me just kind of box these up so that we can kind of keep them straight. So let's go ahead first and, well, why don't we go ahead and solve for the linear acceleration. So what I'm going to do is I'm going to eliminate F. So I'm going to take my second equation here, and I'm going to solve for F there, and then I'm going to stick it in there. So if I take my second equation, I solve for F, I get F equals I alpha over R. And now I'm going to stick that in my first equation. So if I do that, I get mg sine theta minus F, which is I alpha over R, and that should be equal to ma. Well, now I've got A and alpha in here. So I just want to pick one to solve for, right? I don't want to have A and alpha. So I think what I'm going to do is, let's get rid of alpha. Right? And I can do that by using this equation. Right? If I want to solve for alpha, that just basically becomes alpha is A over R. So I can use that, right, to get rid of my alpha and put an A over R there instead. So let me do that. I've got mg sine theta minus I times A over R. This becomes A over R squared equals ma. Now I need to solve for A. It's getting a little ugly here. Equal to ma plus I A over R squared. And I think now is probably as good a time as any to also use the rotational inertia equation to get rid of that I and plug in m and r instead. Right, so I know that I is actually equal to mr squared. And I know that the m and the r are both actually given. And that's going to actually let me cross out that little r right there. And it's going to let me cross out the masses. Probably should have done that earlier in the question. It would have cleaned it up a little bit. mg sine theta equals ma plus, and now I'm going to plug in for I, so that's mr squared times a over r squared. And actually I can just see that I have almost made a mistake. It should be 1/2 mr squared because it's the disk, right, or cylinder, same. And now I can cancel stuff out. I've got an m in every term, and here I've got an r squared and an r squared there. So it does simplify a lot. Now I've got g sine theta is equal to a plus, what was it, 1/2 a? Yes, and now we're solving for a. So if we simplify a little bit more, g sine theta is equal to a times 1 plus 1/2. Right, I just pulled an a. I factored out a from those two terms. And solving, we've got g sine theta equals a over 1/2, which is 3/2. So something like that. Or if I want to simplify it to be nicer, 2/3 g sine theta equals a. So something like that. Cool. Okay, so we've got our a. Now let's keep going. So there's the translational acceleration. Now to get the angular acceleration, right, we just have to come back here. Right, so the angular acceleration is just a over r. So let's do that. So alpha is a over r. Now we just take the a value we got just a minute ago. It was 2/3 g sine theta, but we got to divide that by r. So it's 2g sine theta over 3r. That should give me my alpha. Boom. Okay, last bit. Find the force of friction. Well, we can do that now because we know alpha, we know I, we know r. So if I just take this equation for friction, right, I already solved it there. We've got F equals I alpha over r. I know I is 1/2 mr squared. Let's see, 1/2 mr squared. And that is all being divided by r. And alpha, which we found, 2g sine theta over 3r. That's our alpha. All right, so now again, we've got to simplify a little bit. The r squared actually cancels. The 1/2 cancels too. That's nice. So our friction force comes out to be just mg sine theta. What? No, 1/3 mg sine theta. There we go. All right, so I hope this was helpful. But really, just to come back to the main things that we did here, where we looked at the forces on our object and where they act, and we used those forces to write two equations, one using F equals ma, and one using net torque equals I alpha. Right, this is the net torque, this is I alpha. And then we also use the relationship to relate translational acceleration to rotational acceleration. Notice we also use the equation for the inertia of a cylinder. So all of the physics really happened here, right, when we wrote these equations. Everything else was just sort of algebra. All right, I hope this was helpful, and I hope you can use this to solve other rolling without slipping problems as we move further into this unit.